Welcome to the basics of machining. Now, let us try to see chip breakers. Chip breaker you can try to have integrated in the tool itself, or you can try to have supporting system which tries to break the chip. Why are the chips to be broken? In continuous chip, the chip disposal is a challenge. The chip disposal is a challenge. So, need for a chip breaker is to break the chip and produce small pieces. Small pieces, then it can be collected very fast. The work hardening of the chip makes the work of the chip breaker easy. The work hardening of the chip. So, generally what happens, if you try to go back to the tensile testing, so you see here in this phenomena is called as the strain hardening. So, that is what we say, work hardening of the chip makes the work of the chip breaker easy. When strict chip control is desired, because this continuous chip can also get entangled while machining and disturb the machined surface. So, when strict chip control is required, we can try to have chip breakers as shown here. We can have at the edge, cutting edge, slightly offsetted from the cutting edge, or we can have an external support to the tool. When the chip moves, it tries to hit the clamp and then it tries to break. So, there are three steps. One is step type, the other one is groove type, the third one is a clamp which is given on the top. When the chip moves, the clamp restricts and the continuous chip hits it, and because of that it starts curling and then it tries to break, along with the other type of rake faces you can think of. Now, let us try to go little bit inside and see the forces which are involved in metal cutting. So, why is this? Because everywhere you see, I have been talking about rake angle, I have been talking about rake angle, I have been talking about shear plane, I have been talking about the chip thickness ratio, I have been talking about the velocity. So, all these things are important. Why? Because we have to reduce the forces, and then this leads to power reduction. So, now I can experimentally measure it, but that needs lot of instrumentation and other things. Now, I wanted to calculate how do I reduce the force. So, I wanted to do some small theoretical work and try to figure out how can I calculate the force which comes. Here it is a theoretical idealistic force. So, based on the force I can go back and iterate all the parameters such that my power consumption goes low. So, now what we are doing is we are trying to put effort in understanding the force. How do I calculate the force with respect to the parameters which I give in the machine or I make on the tool. The force acting on the chip during the orthogonal cutting is shown here. You can see here these are the forces which are involved. Let us see what are the forces. Along the shear plane, you will have a force which is acting, which is called as shear force, and normal to that is normal force. Shear force acts along a shear plane, and normal to that shear force is the normal force. So, the resultant of these two are done calculated as R. Now, let us try to, this is on the workpiece zone. On the tool zone, let us see, there is a friction component which happens along the tool chip interface. So, there is a friction force which is called as F, and there is a normal to the friction force is N. When I resolve these two, it is called as R. So, there are two R's. In order to have more clarity, I will try to convert the resultant between Fs and Fn as R dash. The angle between the resultant force R and the normal force is given as beta. beta will be the friction angle, right. So, this is what happens while machining in orthogonal cutting. So, let us go by reading through the slides. The force applied against the chip by the tool can be separated into two mutually perpendicular components, friction force and Fn, normal force. The force applied against the chip by the tool can be resolved into F and N. The friction force is the frictional force resisting the flow of the chip along the tool face. Along the tool face. The tool face is the rake face. That is F. Perpendicular to that is N. The two components can be defined, these two components can be used to define the coefficient of friction which is happening here. Coefficient of friction is nothing but force by N. So, you see mu, coefficient of friction is defined as F by N, or it is given as mu is equal to tan beta. Beta is the friction angle, mu is the coefficient of friction. So, now I can try to find out what is the friction which is coming here. In addition to the two forces acting on the chip, there are two more components applied by the workpiece on the chip, which is nothing but Fs and Fn, shear force and normal to the shear force. The shear force Fn is the force that causes shear deformation to occur along the shear plane, and normal to that is Fn. Using the Fs and Fn, we can try to figure out shear force. So, the shear force which we can try to measure by doing experiments in universal tensile testing machine, we can try to figure out the shear force. The shear force is nothing but shear stress acting along the shear plane divided by the area. So, tau is nothing but Fs by As. Fs is the shear force and As in the shear area whatever is there. So, using the shear force, the shear stress that acts along the shear plane between the work and the chip can be defined as tau is equal to Fs by As. What is As? The area of the shear plane is called as As. How do I calculate the As? As can be found out by T naught into W divided by sin phi. This is T naught, and this is W with this is T naught and this is W. So, As is nothing but T naught into W divided by sin phi. You can try to find out As. Now, we are trying to find out what is the shear force which is coming into action. So, generally tau can be figured out, Fs will be not found out, and As is also you can see here, you can figure it out, right. So, we try to calculate tau is equal to Fs by As. Fs will not be known. So, what we do is As into tau will try to give us Fs. So, that As is nothing but T naught into W by sin phi is equal into tau equal to Fs. So, now I can try to figure out Fs. So, the entire thing whatever is there is being derived into a simple form which is called as merchant circle. Merchant circle force analysis is the very simplistic version through which you can try to figure out what are all the forces which are involved in orthogonal cutting. So, before we get into the merchant circle, there are assumptions which are made, because it is too difficult to do a realistic model prediction. So, we use first principles. The cutting edge is straight and sharp, and it is assumed to continue to be there. The material is homogeneous, there is no impurities, there is no defects. The cutting is orthogonal. The material is rigid and perfectly plastic. So, the response will be perfect plastic. The shear zone extends in a very narrow region which can be approximated to a straight line. So, what we say is, we say the area is very small. Okay, these are the assumptions, and as we have already seen, all of this are there. Now, we will try to draw a circle and then we try to mark all those things. That is it. So, if you see here, this is Fs acting, perpendicular to Fx is Fn. So, now when we resolve Fs and Fn, we get R. So, this R is R double dash or R dash, and the shear plane angle. So, this is the shear plane angle. So, phi, right. Then this is the friction force which come here. This is the rake angle. This is the friction force Ff along the line, and normal to that is Fn, right. So, if you go here, you can see all we have made. So, this is friction force F, normal to the friction force is N, and the angle between these two is friction angle beta. The R is going to be the same for, because it is going to be balancing the reaction force and reaction force are balanced. So, this is R, right. Then this force which acts along this is Fs. Normal to Fs is going to be Fn. So, the angle between Fs and the straight line is going to be theta. This is going to be theta. So, now the rake angle is given here. So, now the angle which is subtending here is going to be friction angle minus the rake angle. Now, if you see what all, we have not done anything new. Fs, Fn you already know, F and N you already know. Then we have already explained phi and angle, right. So, now this has a resultant force R dash, this has a resultant force R. Now, between these two I have introduced a terminology called friction angle beta, right. And then between Fs and Fn I have introduced a terminology called nu. So, these are the forces which are there. Now, from this I will have to find out what is the cutting force which is required while machining, right. So, that is the force which cutting force. The cutting force is Fc, and the thrust force which comes because of this is Ft. So, now I have introduced Fc and Ft. Fc is cutting force because the resistance given by the tool or resistance given by the tool on the chip, that direction is Fc, cutting force, and perpendicular to the cutting force is Ft. Now, we have found out cutting force and tangential force. So, rake angle is known, friction angle is known, shear angle is known, then shear force is known, then cutting velocity is known. We have already seen V equal to pi dn. The chip velocity is known, shear velocity we will see, friction force is known, and normal to the friction force is known. So, what is not, till now it is not known as cutting force and thrust force. What is cutting force? When the tool is acting, the force which is resistance given is Fc here, and perpendicular to Fc here is Ft. So, this too is also known. So, now what is the other thing which is not known is the shear velocity. Shear velocity is which the velocity, the shear moving shear plane moving with a velocity is called as Vs. Now, with this we will try to form an interlink such that we can try to calculate the cutting force. So, this diagram is called as merchant circle diagram. Why there are 3 R's? R1, this R is between Fs and Fn. The next R is between F and N. The third one is between Fc and Ft. So, the resultant of all the 3 are equal, and that is how we try to draw this merchant circle diagram. Now, let us try to do the force analysis. Equation can be derived to relate the 4 force components that cannot be measured to the 2 force that can be measured. So, what cannot be measured are Fn cannot be measured, Fs cannot be measured, Fn cannot be measured, and F cannot be measured. This cannot be measured. What I can measure is only Fc and Ft. Now, I have to connect this with respect to this. So, if the cutting force and the thrust force are known by some dynamometer, these 4 equations can be used to calculate, estimate the shear force, friction force, normal force to friction force, to friction. Based upon the forced estimate, the shear stress and the coefficient of friction can be calculated using this force diagram. Using trigonometry, we will try to figure out the relationship between F, N, Fs, Fn with respect to Fc and Ft. So, F is equal to Fc sin alpha and Ft cos alpha. You can try to solve it. If you have difficulty, we will see in the tutorial. N can be related with Fc cos alpha minus Ft sin alpha. Fs can be Fc cos phi minus, because these 2 are known to me, alpha rake angle and friction angle and shear angle, Fc into cos phi, Ft into cos phi. Then Fn will be Fs sin phi plus Ft cos phi. So, now Fc and Ft can be written like this. So, it can be written like this, and where S is the shear stress, this is tau, right, tau. So, you remember we wrote Fs by As is equal to tau, right. Now, Fs is nothing but tau into As. So, that is what is come here, right. So, S shear stress into tau also comes here. So, that area we multiply and then we write it like this. So, this is nothing but Fs cos beta, beta is nothing but the friction angle minus the rake angle divided by shear cos shear angle plus friction angle minus the rake angle. So, we can try to calculate the Fs and Ft. So, now these 2 parameters are known. I do not know 4 parameters. Now, I have linked all of them by using the merchant circles diagram. So, the merchant circle equation can be finally written like this. The merchant reasoned that out of all possible angles emanating from the cutting edge of the tool at which the shear deformation could occur, there is one angle called phi that predominates shear plane. This is the angle at which the shear stress is just equal to shear strength of the shear stress is just equal to the shear strength of the material. And so, shear deformation occurs in this angle. So, shear angle is equal to 45 plus rake angle divided by 2 minus friction angle divided by 2. This is merchant circle equation. So, this is from orthogonal cutting. So, here it is very close or very close to oblique. It has quite a lot of approximations, and by and large by using the first principles, you can try to have a rough approximation of the forces. So, that is why merchant circle equation and merchant circle diagram is very important while teaching metal cutting. There are advancements which were done by little more researchers. Ernst and Merchant, Ernst joined along with the Merchant's theory, or he modified the Merchant theory, and then he brought in an equation like he brought the relationship between shear plane, rake angle and friction angle for minimum power consumption should be written in this way. And then he did the second analysis, he presented it like this way. So, where K is the machining constant, which depends on tool material combination for K. So, the next advancement, see people started, see the original value is here, the theoretical merchant circle value is there. So, now merchant circle, next came Ernst and merchants theory, then came Lee-Schaffer. So, they are all trying to go closer to the original or to the experimental value. The theory of Lee and Schaffer was the result of an attempt to apply plasticity theory to orthogonal metal cutting. The assumptions were the work material ahead of the tool behaves in an ideal plastic. So, here if you see, we assumed it as a rigid, we assumed it as a material is rigid and perfectly plastic. So, here he assumed it that it is ideal plastic mass. There exists a shear plane which separates the chip and the workpiece. No hardening in the chip occurs. So, then based on the assumption he came up with this obtained, and the shear and the slip lines meet the surface at 45 degrees. These were the assumption made. So, by and large, the important thing is you have to remember that there is a relationship between shear plane, rake angle and friction angle, which was expressed by Merchant and which was further fine tuned by Ernst. And then Lee-Schaffer, by changing the material behavior to ideal plastic mass, came up with this relationship. So, all these things give a relationship between shear plane, friction angle and rake angle. That is important for you. Now, let us try to find out the relationship between cutting velocity and the chip velocity. See, cutting velocity is nothing but V. When this V happens along the shear plane, it is called as shear velocity, and when the chip moves, it is called as chip velocity. So, let us assume that the work material is moving against the cutting tool with a velocity of V. What is V? Pi d n. 60, 100 depends upon a minute, second, whatever it is. The velocity, the chip velocity Vc is the vector sum of V, the velocity of the uncut chip and the shear plane. So, if you see here, we are trying to plot the velocity diagram. So, velocity diagram, this is V and along the shear plane is Vs. So, this is Vs, velocity along the shear plane, this is a typical V pi d n. Now, we have to find out the relationship between V, Vs with respect to Vc. So, this is the chip velocity normal to Vs and to V, we try to draw a normal and that is called as Vc. The shear plane angle is the angle between V and Vs. We already know the rake angle alpha. So, that when you draw a normal to Vs which meets at V, that 90 degrees whatever you draw is called rake angle. The angle between the normal and the shear velocity is 90 minus alpha. So, this is 90 minus alpha and this is alpha. And just so, since this is alpha and this is 90 degrees, this angle is 90 minus alpha. So, since this is 90 minus alpha and we try to draw a normal, then that angle becomes rake minus phi. So, applying the sine's rule, V velocity is divided by sine minus 90 minus phi plus alpha. We use sine's rule. So, this is equal to Vc by sine phi and that is equal to Vs by sine 90 minus phi. When we try to equate this, it becomes like this: V by cos phi minus alpha is equal to Vc by sine phi, that is equal to Vs by cos alpha. So, now all these things, why is it important? Now, you have almost everything theoretically ready. What are they ready? F, N, Fs, Fn, Fc, Ft, phi, alpha, beta, you have this at one side from the merchant circle diagram. Now, we have found out the relationship between V, Vc and Vs. So, with all these combinations, you can try to calculate power. Y is power. Ultimately, I have to find out what should be the minimum energy I apply such that I get the required output. So, cutting power can be figured out from Fc into V. Fc is the cutting force which we can measure multiplied by velocity. The shear power can be found out by Fs into Vs. Vs can be figured out from here, Vs by cos alpha, we can try to figure out. So, that tries to talk about the shear power. Friction power, if you want to do, that is nothing but F into Vc. So, the cutting power Fc into V is nothing but shear power plus friction power, which is Fc into V is equal to Fs into Vs plus F into Vc. So, what is specific cutting power? Specific means it is always with respect to a unit. So, it is said as cutting power divided by unit material removal, or you try to put material removal so that you can try to figure out what is specific cutting power, Fc into V divided by material removal rate. So, now material removal rate can be figured out by width of the chip T1 into cutting velocity. So, now so the specific power will be Fc into V by W T1 into V. So, this V goes off. So, it is Fc by width into T1. So, this tries to give you the specific cutting power. Specific cutting for a unit amount of material, what is the power required is the specific cutting power. So, the power consumption is, I have already dealt, it is a product of Fc into V. So, the material removal rate can be calculated as V into T naught into W. So, here it will be T naught, do not get confused, it will be T naught, T naught. So, the equation can be written as unit power is equal to this divided by unit amount of material is this. So, we can try to calculate the for Fc is given in newtons, V is given in meters per second, specific unit is given in Newton meter per millimeter cube. So, the power consumption is nothing but the millimeter cube. So, here you can see that I have given you various material, what are their hardness, what is the unit, what is the force, what is the unit power consumption, unit energy required for material removal. So, the cutting temperature, the next topic of discussion is going to be cutting temperature. As I told you, cutting temperature is one of the very important phenomena because it is metal to metal cutting, friction there, and this friction deforms the workpiece, softens the tool, so you try to avoid it. So, it is always good to find out what is the cutting temperature. The equation can be used to predict the increase in temperature at the tool tip is delta T is equal to 0.4 times U. What is U? U comes from specific energy divided by rho, which is a material property, and C is also a material property, and V is the cutting velocity, T naught is the uncut chip thickness divided by K. K is a constant to the power 0.33. This is relationship is got from empirical analysis. So, where delta T means the mean temperature rise from the room temperature to that, then U is the specific cutting energy operation which we have seen, V is the cutting speed, T is the chip thickness before cutting, Pc is the volumetric specific heat of a given material, K is the thermal diffusivity. So, all these things are physical properties. It is volumetric specific heat multiplied by thermal diffusivity of the workpiece. So, then finally, we try to get a relationship as T is nothing but K times V to the power m. So, final point of discussion is going to be tool wear. Because of the friction, there is going to be a deformation which is happening on the tool. So, now let us try to discuss about the tool wear. If the tool wear happens, then the tool geometry changes. If the tool geometry changes, the surface finish what generates is not good, and the forces might go high. So, tool wear is a gradual phenomena. Tool break can happen, tool wear can happen. Wear is a continuous phenomena. Tool wear is a gradual process created due to high localized stresses at the tip of the tool. Here there are very high temperatures, the sliding of the chip along the rake face produces friction, sliding of the tool along the newly cut workpiece is also there. All these things lead to tool wear. The rate of tool wear depends upon tool workpiece material, tool geometry, process parameter, cutting fluid what we use. So, these are the measures which we take to reduce the tool wear. So, generally in a tool we have a crater wear and a flank wear. So, crater wear happens along the rake face. The flank wear happens along the cutting edge. It consists of a cavity in the rake face of the tool that forms and grows from the action of chip sliding against the surface. The high stress and temperature characteristics characterize the tool chip interface, contributing to a wear action. The crater is very difficult to measure because it is erratic in nature and the depth also is erratic. So, we have to measure the depth to do it. Generally, what we measure is the flank angle. The flank angle happens along the relief face, flank relief face. So, here as and when the cutting happens, there is a gradual wear. So, if you see here, I have linked it, what is the feed which is given and what is the depth of cut which we give with respect to machining, feed, depth of cut, and now what you do is you try to figure out what is the amount of wear which has happened. So, we say flank wear, and then if there is a sharp dip, it is called as notch wear. So, this is the nose radius. So, now you can try to see on the rake comes the crater, on the cutting edge relief there comes the flank wear. So, the factor influencing for crater wear can be temperature. This temperature leads to diffusion. So, this diffusion heat is there. So, we saw that in heat treatment we saw there is a diffusion happening, right. There is a diffusion which happens, and because of this diffusion there is a chemical difference, and that leads to a wear. The chemical affinity between the tool and the workpiece material happens. The diffusion rate increases with increase in temperature, which relates to the crater wear. There is an increase, and then the localized the location of the maximum depth of crater wear KT coincides with the location of the maximum temperature of tool tip interface. So, what happens is wherever there when the machining happens, the chip goes like this. So, here the temperature is maximum, the crater wear is also maximum. This is the chip. Okay. So, crater wear with respect to tool chip interface temperature, we have just plotted it here. The nose wear which is also there, but it is very difficult to measure. So, as a consequence of a harder surface, the wear accelerates in at its location. The second region of flank wear can be identified is at the nose radius. So, here. So, flank nose crater. It is very difficult to measure. We always try to measure the average points and then we try to do it. There is notching and plastic deformation which happens on the tool tip. Extreme conditions of the flank wear often appears on the cutting edge at the location corresponding to the original workpiece. There can be a possibility of chipping of the tool also happens when the forces are very high. So, here it tries to give you a lot of understanding. So, A refers to the feature of the tool wear in turning operation, B talks about flank wear, C talks about the crater wear, D talks about the thermal cracking which is formed on the flank, and the E talks about built up edge. This is the built up edge on the top of the tool which is there. So, the mechanism generally can be abrasion, adhesion and plastic deformation. Abrasion is with these hard particles when they are moving, hard particles built up edges, they dissociate and they are hard particles between chip and the tool, wherein which they try to create a scratch. This scratch on acceleration tries to chip off. So, that is abrasion. Adhesion is when there is a very high temperature between the chip and the tool, there is a thermal affinity happening and there is a diffusion happening. Because of this, there is a wear. So, when two metals are forced in contact with high pressure and temperature, adhesion occurs. Right. This condition are present between the chip and the rake face, and this is what I said. The plastic deformation is because of the very high temperature which is there, and when the chip is trying to move, that the softening happens at the tool, which leads to plastic deformation. Very high temperature leads to plastic deformation. Diffusion is the temperature between the tool and the workpiece is very high. So, there is a transfer of atom from the chip to the workpiece, where there is a higher temperature, there diffusion happens. So, this follows the Humery rules. The atom gets diffused from the carbon, the carbon atom gets diffused from the steel into the tool material. So, by doing so, what happens? The workpiece becomes hard and brittle. The chemical reaction is almost the same thing with respect to diffusion. So, if we plot the tool life is very important, like finding out the tool, the cutting power. So, here we try to find out the tool life. The tool life is a gradual phenomena. Tool life means finding out the tool wear. It is tool wear is gradual phenomena. I divide the plot into 3. The initial one is called as running in wear, then it is called as uniform wear, then it is called as failure region or a sudden failure region. So, it is divided into 3 zones: zone 1, zone 2 and zone 3. Zone 1 is whatever is the asperities on the tool gets removed and it slowly the tool starts wearing. And in zone 2, we try to have a uniform wear rate with respect to time. And once it reaches a limit, then there is a diffusion. So, generally what happens at this point, the people will try to take the tool back and then they try to grind it. They then bring back the geometry back to original, then they get into this zone. But once it goes into this zone, it is going to be a catastrophic failure. So, zone 1 and zone 2 are comfortable. So, when this is the tool flank wear with respect to time. So, here we try to V is equal to at a cutting velocity of 100, at a cutting velocity, how is this curve? 130, 180. When we go for a higher cutting speed, what happens? The tool life reduces. The temperature goes very high, all the wear phenomena happens. So, this tries to tell as and when the velocity increases, the tool life decreases. So, at whatever I have discussed here, I have presented it in this slide. So, tool life equation, when I take the same thing, same plot and I try to do a logarithmic plot. So, it tool life, tool cutting speed versus tool life. I try to take the log value and then I plot. It comes as a straight line, and moment it comes as a straight line, I try to express an equation. So, with this equation, I can try to figure out what will be at what velocity, what will be the tool life time, and C is a constant which is between workpiece and tool. There is a constant which is already expressed. So, this equation was expressed by F.W. Taylor, or it is otherwise called as Taylor's tool life equation. So, if the tool life value for the 3 wear curves are plotted on a natural log graph of cutting speed versus tool life, then we get a straight line. So, the n value we get it from the slope. So, with this we can try to figure out what will be the life of the tool with respect to the cutting velocity for a given set of combination C. So, the factors which are affecting tool life: material of machine, surface quality, tool material, geometry, tool, machine variables, coolants and cutting tools with respect to vibration. So, all these things are factors which affect Vt to the power n equal to a constant. That is what we say tool life, Taylor's tool life equation. So, now let us understand single point cutting tool and multiple point cutting tools. Single point cutting tool, the cutting tools can be classified into single point and multiple points. Single point means where there is dominantly only one cutting edge. The point is usually rounded to form a nose radius, and it is generally used in turning operation, turning, boring, it is used. When there are more number of cutting edges, it is called as multiple cutting edges. So, here motion relative to work achieved by rotating is done. So, drilling, milling are multi-point cutting tools. Abrasive is also a multi-point cutting tool. So, what is the classification of single point cutting tool and multiple point? It contains only one main cutting edge in the cutter body. It contains more than one cutting edge in the cutter body. The material removal action at the time in a single pass, simultaneously engaging in cutting in a pass. So, it is material removal at a time in a single pass. Here multiple edges will be there. Material removal rate and the production rate are low, here it is high, because at any given point of time, two or more cutting edges will come in contact. Design and fabrication of a single point cutting tool is easy, here it is slightly difficult. The rate of heat which is generated and subsequent rise in tool temperature is very high in a single point. Since the heat is getting distributed, the heat generated is low. So, the tool wear is always low. Usually low feed rate and depth of cut is employed when machining is carried out in a single point cutting tool. Here we go with a higher feed rate and higher depth of cut. So, under this classification of single point, turning, shaping, planing, slotting, fly cutting, fly milling cutters, etc., boring comes into action. Here it is milling, hobbing, broaching, grinding, reaming, all these things come into action. So, single point and multiple point classifications are given here. There are various tool materials which are available. When we look at tool material, we saw about single point and multiple point. When we look at tool material, it is not only one material, there are a spectrum of material which is available. So, it is tool steel, high speed steel, carbides which are ceramic materials, abrasives are used, diamonds are used, artificial diamond and natural diamond is used, cubic boron nitride is used. So, ceramics, tool tips and coated tools. These are all different types of tool material which are available today. So, if you see plain carbon steel has a hardness of 60. When you try to write a tool, what are all the major properties of a tool is it has to have a high hot hardness. Hot hardness should be very high. It has to have a wear resistance property should be high. Hot hardness is at a very high temperature, the hardness should be maintained. The wear resistance should be also very high. These are basic properties. So, hardness at room temperature hardness is different from hot hardness. So, if you see the hardness is put for varying material, so you can try to understand what is it, and it also have to be tough, because when there is a vibration, the tool should not break. So, it has to have high toughness, it has to have high wear resistance, high hot hardness. So, these three properties are very important for any given cutting tool. So, toughness, hardness and wear resistance are the most important property for any given tool material. So, you can see here there is a plot of hardness with respect to temperature. You see how is the hardness property dipping down. So, that is why we try to talk about a property called hot hardness. So, you can see for cast cobalt alloy, then you can see for cemented carbide how is the response. How is the response for ceramic? So, when it goes for ceramic, the toughness is very low. So, we try to use it for as a tip. So, if this is a tool, only this portion will be made out of ceramic. Okay. So, the most important properties for a cutting tool are toughness, hot hardness and wear resistance property. These are high speed steel tools, tool material, and these are the tools. There are a display of tools what we show here. Here if you see the geometry of the tool is complex. So, high speed steel gives you a flexibility of defining the geometry and producing typical difficult geometries for the tool. One of the most commonly used tool material is HSS. So, especially suited for applications involving complicated tool geometries such as drills, taps, mills and broaches, we always use it. So, when we talk about tungsten carbide and molybdenum type, so they are T type, T grades and M grades which are there. So, in HSS itself we have T grades and M grades. So, these are all typically alloyed ingredients. So, we have tungsten and molybdenum included, vanadium and chromium included, cobalt of course, carbon of course and cobalt. So, these are all for tungsten carbide. Okay. Okay, so I redo it here. Two basic types are which is defined by AISI. So, tungsten type which is said as T grade HSS and molybdenum is M grade HSS. The typical alloys which are included in HSS are tungsten, molybdenum, chromium, vanadium, cobalt in some cases and carbon of course is introduced into the material such that it can be harder than the workpiece and you can try to define geometry. Typical composition for grade T1 is 18% W, 4% chromium, 1% vanadium and 0.9% carbon. When we talk about tungsten carbide, the tungsten carbide are class of hard tool materials based on tungsten carbide used as a powder metallurgy technique along with cobalt as a binder. So, there are two types here, which is only tungsten carbide and cobalt. For non-steel cutting grade, we use this. For steel cutting grade, we have along with this the other alloys of titanium carbide and tantalum carbide added. So, when you add these alloying elements, it makes sure that you retain hot hardness, wear resistance and toughness. Cemented carbide general properties, it has high compressive strength, but low to moderate tensile strength. So, toughness will be very low, high hardness will be there, greater hot hardness, greater wear resistance, E is very high and the toughness is lower than HSS. That is why if you see all the HSS tools will be large, you will have a shank and other things. If you see tungsten carbide, these are all tool tips only made. So, only the cutting edge will be made and this will be placed into a shank where there is a toughness property. So, non-steel cutting grades are used for non-ferrous metals and grey cast iron. The properties determined by grain size and cobalt content are there. As the grain size increases, the toughness increases, hot hardness decreases, right. When the grain size increases, the hardness decreases, but hot hardness also decreases, but the toughness increases. So, we have to decide when we use a powder metallurgy route, tungsten carbide powder size is very important. That is what we said here. And the binder, because if you have only ceramic, you need a binder. Cobalt is used as a binder, which also tries to give hot hardness property and wear resistance property. The steel cutting carbide grades are titanium carbide and tantalum carbide are added. So, the composition increases the crater wear resistance to cutting steel. Cemented tools are also there. It is a combination of TIC, TIN, TICN with nickel or molybdenum as a binder. So, again here it is an insert which is used for making it. So, friends, if you try to take solid tools will be HSS, all the other tools are inserts. Higher speed and lower feed can be used with steel cutting grade, better finish can be achieved. When we talk about coated carbide, so even if you want to improve the resistance of your insert, we can give a coating. So, a coating of TIC, TIN or Al2O3 can be given or multiple layers can be given such that it tries to enhance the property is coated carbides given here. Coating applied by chemical vapor deposition or by physical vapor deposition, which tries to enhance the tool material property. Ceramic is on the higher end. So, HSS, we have solid tools, then we have tungsten carbides, then we have ceramides, then we have ceramics. Okay. So, these all are inserts. So, on top of a solid tool or a insert, we can try to give a coating. The coating is only to avoid the thermal diffusion. Primarily, fine grain Al2O3 pressed and sintered at high pressure and temperature is formed without a binder. You can get it in ceramics. They are highly recommended for large depth of cut machining and exotic material machining. Synthetic diamond is also used as a tip. So, now these all are synthetic diamond is also a tip. Sintered polycarbide diamond fabricated by sintering very fine grain diamonds crystals under high temperature and pressure into a desired shape with little or no binder is done with synthetic diamond. Natural diamond, synthetic diamond. Carbon, very high temperature, very high pressure, what you get is a synthetic diamond. So, usually applied as coatings on this insert to get a better property. CBN is next to diamond. Diamond is the hardest, next to cubic boron nitride, which is the hardest material known. The fabrication into cutting tool inserts, same as SPD, is done here. It is application of nickel machining, titanium machining can happen by using CBN. So, the application of metal cutting is found in various industries, automotive industries where there are complicated parts, aerospace industry, construction industry, energy industry where you have gears to be made on a wind turbine, medical industry where small plastic gears have to be made, the die has to be made, electronic industry and consumer product industry. Everywhere where there is a complicated process, where the depth of cut is very high, we try to use metal cutting process only. To recap, in this entire machining lecture, what we have seen is, we have seen the introduction of machining, classification of machining. We have seen single point cutting tool, the rake angle, flank angle, and then the 6 angles with nose radius. Then chip, how does a chip form? What is the chip forming mechanism? What are all the forces involved in metal cutting? Then we went into merchant circle diagram, cutting fluid requirements, then we saw about the tool material. These are the references which we have used in preparing this lecture. Thank you very much.